Hi, welcome back. In this segment, I'm going to talk about an interesting exercise related to double encryption, meaning you encrypt a message M using, say, key K1, you get some ciphertext. You take the ciphertext and encrypt it again using, say, another key K2. I'm going to ask, is this is this of any value? Okay, and I wanted to instantiate this problem using the Swift cipher, which we discussed earlier. The problem is formalized here in this exercise, right? Alice and Bob are using the modified version of Swift cipher. They call it 2-Swift. Okay, and 2-Swift is formally defined here. It takes three arguments, K1, K2, and the message M. K1 and K2 are the two keys, and M is the message to be encrypted, for example. And M could be hello or whatever message you would like to encrypt. And how is 2-Swift encryption defined? It's nothing but calling the encrypt function. First, we encrypt the message M using the key K1. So you get some ciphertext from this. And then we encrypt that using key K2 to get a ciphertext C. Okay. And the decryption goes as follows. Of course, we need to first decrypt the ciphertext using K2. That's the reason why K2 is put inside. And then we decrypt it using K1. Okay, this is how the decryption is defined. All right, and the encryption and decryption functions are just basic Swift cipher functions that we talked about earlier. Okay, the question is very simple. Is the key space 26 power 2 size to brute force? Because we're talking about two keys, K1 and K2. Since we are talking about mod 26, meaning the key has to be an element from 0 through 25, we are taking two keys, K1 and K2, right? So it's natural to ask, is the key space 26 power 2 for brute force, or can we do more efficient? That's basically the second problem, right? It turned out that this problem can be of a somewhat of tricky one for folks who are not familiar with modular arithmetic. So hopefully I will clarify in this segment, okay, why I think that we can brute force not using 26 power 2, but much more less, meaning just using at most 26 atoms, we can still brute force, even though we have two keys, K1 and K2. So, okay, let's proceed now with the demo. All right. So what I'm going to do is show to you my demo. Let's consider a message. Say the message is, I have already prepared a message for the demo purpose. Message. So this is the message. So let's take one key, for example, the first key to be some number, say 3, and the second key to be, say, some number 5. Okay, we need two keys. Now let's apply Swift cipher on this message, first using K1 and then encrypt it using K2. Okay, so we're going to find the first ciphertext by calling the Swift cipher encryption of the message and the key K1. Okay, and then we do again encrypt, but using the ciphertext C1 using key K2. Okay, so we can now check whether our algorithm works correctly by decrypting it, of course. Excuse me. So let's decrypt the Swift cipher algorithm using the Swift cipher algorithm. First, we need to pass C2 because that's the outermost thing, which was decrypted using K, which was encrypted using K2. Therefore, we need to decrypt it, and then we will decrypt this again using key K1. Okay. So as we can see, we get back exactly what we encrypted. So the algorithm itself is correct. But from a brute force perspective, I want to show you something interesting. Let me show you what is the value of the ciphertext C2. Okay, this is the gibberish value we get by double encryption. Okay, we encrypt a message, we get the output, we encrypt the output again using a different key. That's basically the double encryption in this case. So let's see what happens if you actually print enc Swift cipher directly using the key K1 plus K2 in mod 26. In this case, it doesn't matter because K1 plus K2 is already less than 26, but I just will put it for you. Okay. You see here, I get exactly the same ciphertext. That means if you take the original message that was given to us and encrypt using this key 8, instead of key 3 followed by key 5 as we did above, we get the same effect. That means it should be possible to brute force using only one key, which I'm going to do now. I have written my brute force, which we talked about earlier. So I will be using my brute force attack. Let's take basic brute force. Okay, so I'm going to brute force C2 now. C2 is the ciphertext we got from double encryption. Right, let's do the brute force of C2. Okay, so let's look for our text. Is double encryption in use? That was the text. Where is it? Yeah, here it is. Is double encrypt useful? So it's part of the brute force. We can actually do much more better brute force using the index of coincidence we talked about earlier. So let me do index of coincidence. As you can see, the brute force is only trying all possible key k from 0 through 25, including 25. That's the main point I wanted to convey, that we don't have to do 26 for 2. It's enough to just try 25 combinations, 26 combinations. Okay. So let's now do brute force with the index of coincidence. Let's set the minimum IC value to be 0050. And we can see that is double encrypt useful when the key is 8. It was automatically able to find the key. Of course, this was not the key they used. They used K1 followed by K2 when encrypt, but it doesn't matter because it's equivalent to key 8 anyways. What I have shown to you in this short demo is that sometimes double encryption is not useful. In this case, we have a weak cipher, CIF cipher, of course. We encrypt once and then we encrypt the output again using a different key, which has no effect, although it looks from outside that we have 2 keys, but the effect is just same as 1 key. This is an interesting problem, even in AES or DES. What is the value of double encryption? Okay, how much benefit you get from double encryption? Okay, not necessarily much when you do double encryption. All right, thank you very much.